Right now, as you're watching this, 6 states are under critical fire weather conditions at the same time. The relative humidity over the Texas and Oklahoma Panhandle has fallen to 4%. Wind gusts on the Mojave Desert Slopes are forecast to 70 miles per hour. The fuels across roughly a third of the lower 48 states are drier today than they have been on 9 out of every 10 mid-May days in the modern observational record. The National Weather Service has 26 red flag warnings active simultaneously. Every megafire in modern American history started under conditions less severe than what is operationally active across the western United States right now. The drought made the loaded gun. 2 heat domes cured the fuel. The wind is here, and the fire season has not officially started yet. So what happens between this afternoon and the start of August, when the actual peak of the season arrives on top of fuel that is already operationally pre-staged for it? If this got you locked in, take a second and hit subscribe to the Sky Lab. We are tracking this fire weather window every day until it closes. Drop a comment with where you're watching from and whether you can see haze, feel the wind, or smell smoke in your air today. I read every single one. And share this with someone who lives in the warning corridor. They need to see what is on the field right now. Let's get into it. Part 1. The conditions that started every megafire in American history are active right now. Right now, as you're watching this, 6 states are under critical fire weather conditions at the same time. The relative humidity over the Texas and Oklahoma Panhandle has been forecast to fall as low as 4% this afternoon. The wind gusts on the Mojave Desert Slopes are forecast to reach 70 miles per hour. The fuels across most of the affected geography are measuring at the 90th percentile of the historical dryness record for this date, meaning the vegetation across roughly a third of the lower 48 states is drier today than it has been on 9 out of every 10 mid-May days in the modern observational record. The National Weather Service has 26 red flag warnings active at the same time, accompanied by 8 fire weather watches that escalate the regime through Monday. The Storm Prediction Center has issued the maximum operational fire weather designation available short of declaring an extreme day, with 3 risk categories live simultaneously, including an isolated dry thunderstorm risk that places a natural ignition source directly on top of the dry fuel corridor. And the part of this that the operational fire weather meteorologists keep coming back to in their morning discussions is that fire season has not officially started yet. The corridor begins at the southern Sierra Nevada in California, runs down through the entire Mojave Desert, crosses the state line into Nevada and Arizona, sweeps east through every fire weather zone in northern Arizona and most of New Mexico, and terminates in the Texas and Oklahoma Panhandle. It is not a collection of separate warnings issued by separate offices that happen to fall on the same day. It is one continuous warning corridor that runs roughly 1,500 miles from west to east, and spans approximately a third of the contiguous United States in a single afternoon. There is no recent precedent for an unbroken red flag warning corridor of this footprint in mid-May. The geography you're looking at, on the map the National Weather Service drew this morning, is the geography that historically lights up in late June, in July, and in August. Not in the middle of May. The numbers underneath the map are what make this a video and not just a weather story. In the National Weather Service Amarillo Zone, which covers the Texas and Oklahoma Panhandle, the morning discussion calls for southwest winds today of 10 to 25 miles per hour, gusting to 30, and on Sunday escalating to 20 to 35 miles per hour, with gusts to 45. Relative humidity is forecast to fall as low as 4%. Temperatures today will reach the mid-90s to the low 100s. The energy release component, which is the metric the National Fire Danger Rating System uses to express how much heat the fuel matrix will release if it ignites, is sitting at the 90th percentile of all historical values ever recorded for this date in this region. Fuel that is at the 90th percentile is fuel that is operationally indistinguishable from peak summer dry fuel. It is not damp, it is not curing, it is cured. A few hundred miles to the west, the National Weather Service Hanford office in California issued a red flag warning at 3:57 in the morning Pacific time, covering the west side hills along the coastal range and the entire San Joaquin Valley. Wind gusts are forecast to 35 miles per hour Saturday and Sunday. Relative humidity is forecast at 20% or less Saturday and Sunday, dropping to 15% or less Monday. The same Hanford office issued a separate red flag warning for the Indian Wells Valley and the Kern County Desert, which sit just east in the Mojave proper. Inside the Mojave, the The forecast is for west winds 20 to 30 miles per hour with gusts up to 45. On the Mojave Desert Slopes, where the terrain accelerates the downslope flow, the forecast escalates dramatically. West winds of 35 to 45 miles per hour, gusts up to 70 miles per hour, relative humidity 10 to 20% at minimum. The companion high wind warning for the Mojave Desert Slopes, which the same office issued at 3:47 Pacific Time, is one of the bluntest pieces of operational warning language the National Weather Service produces. The text reads, and you can pull this up yourself, damaging winds will blow down trees and power lines. Widespread power outages are expected. Travel will be difficult, especially for high-profile vehicles. Now think about what those 3 sentences mean when you place them on top of a fuel bed that is at the 90th percentile of historical dryness, with relative humidity in the low teens, in a region where every active power line within the warning footprint is being shaken in winds approaching the structural rating of the line itself. Damaged power lines are one of the leading single causes of California wildfire ignition in the post-2018 era. The Camp Fire that destroyed Paradise, California in November of 2018 and killed 85 people was ignited by a failing electrical transmission line under exactly this combination of wind, humidity, and fuel. To the north, the National Weather Service Sacramento office issued a red flag warning at 2:11 Pacific Time covering south-central Shasta County, including the Redding metropolitan area. North winds 20 to 30 miles per hour, gusts 35 to 45 miles per hour, locally up to 50 miles per hour around the Delta and the western Sacramento Valley. Daytime minimum humidities of 7 to 15%. Overnight maximum humidities of only 20 to 50%, which is the part the forecasters quietly underline, because that overnight recovery range is too low to give the fuel any meaningful rehydration window before the next afternoon's heating cycle starts the dry down again. The Redding metropolitan area sits inside this warning corridor. Redding is the same metropolitan area that, in July of 2018, lost just over 100,000 acres of surrounding land and 7 lives to the Carr Fire, a fire whose most documented behaviour was the development of a fire whirl. A fire whirl, in scientific terminology, is a vertically organised vortex inside a burning fuel column. The Carr Fire whirl was so powerful, so structurally coherent, that its damage was rated by post-event field surveys at the equivalent of an EF3 tornado. It uprooted trees, threw vehicles, and stripped the asphalt off the road surface in patches. That happened in the Sacramento Valley. The forecast today for the same valley has the same wind, the same humidity, and a fuel state that is drier today than it was on the day the Carr Fire ignited. Across northern Arizona, the National Weather Service Flagstaff Office issued red flag warnings at 12:50 Mountain Time, covering the northeast plateaus and mesas, the Little Colorado River Valley across Coconino, Navajo, and Apache counties, the Painted Desert, the eastern Mogollon Rim, and the Black Mesa area. The today warning calls for southwest winds 15 to 25 miles per hour, with gusts 30 to 40, and relative humidity between 8 and 17%. The Sunday warning escalates the same zones to winds of 20 to 30 miles per hour, gusts 40 to 50, and humidity of 10 to 24%. A separate Sunday red flag covers the Kaibab Plateau, the Marble and Glen Canyons, the entire Grand Canyon country, the Chinle Valley, the Chusca Mountains and Defiance Plateau, and the White Mountains. The geography here matters. These are the elevations where, historically, fire activity does not begin until late June or July. The fuel matrix in juniper and pinon ecosystems is normally still carrying winter moisture into mid-May. This year, the spring snowpack across the Colorado Rockies and the Sierra Nevada was below normal at peak winter accumulation. The early spring dry down was accelerated by 2 consecutive heat dome events in March and early May, and the result is that the high elevation fuel matrix is already operationally ready in mid-May, at a level it normally does not reach until at least mid-June. The Tucson office, the Las Vegas office, and the Grand Junction office in Colorado all issued morning red flags carrying comparable wind, humidity, and impact language. The Albuquerque office issued a red flag covering the Middle Rio Grande Valley, the Sandia and Manzano Mountains, the Central Highlands, and the East Central Plains, citing strong winds and low humidity, stretching from the Rio Grande Valley eastward into Texas, with a Sunday fire weather watch extending the regime across most of west central, eastern, and northeastern New Mexico. The El Paso office issued a fire weather watch for Sunday, covering the southwest mountains, the southwest deserts and lowlands, the south central lowlands and southern Rio Grande Valley, the Capitan and Sacramento Mountains, El Paso itself, and Hudspeth County, with temperatures forecast in the upper 80s to lower 90s and relative humidity falling into the single digits. And then, just to make the geographic spread of this even stranger than it already is, the National Weather Service Gaylord office in northern Lower Michigan issued a red flag warning at 9:29 in the morning Eastern Time. Northern Lower Michigan, in May, critically dry air behind a frontal passage, southwest winds gusting to 25 miles per hour, and afternoon humidity dropping to 18%. That warning is the outlier on the map, the geographic anomaly that tells you the air mass driving this regime is not localized. The same dry air pulse that is delivering the Mojave gusts and the Texas Panhandle 4% humidity is reaching into the upper Midwest with enough strength to put a red flag warning on the map of a state that historically does not see red flag conditions in May. To put the geographic footprint into perspective, consider what is normally on a National Weather Service red flag warning map on May 16th. In a normal year, you might see 1 or 2 warnings in the southern plains, and maybe a small cluster in California or Arizona. The total area under warning is usually a few percent of the lower 48. Today, the total area is approximately a third of the lower 48 states, spread across a continuous corridor with 26 separate warnings, 8 watches, and a Storm Prediction Center outlook that has the maximum operational designation for a non-extreme day. The historical reference point for an event of this footprint is not last May. It is not any May. It is the kind of regime that historically occurs in late June through August, the climatological peak of western fire season, and that is the part that, when you sit with it, starts to feel different than a normal weather story. The relative humidity, the wind gusts, the fuel state, the ignition risk, the geographic spread, all of these operational signals individually would be remarkable for May. Together, they are not remarkable. They are an outlier event so far outside the normal mid-May distribution that the operational language inside the morning discussions has stopped calling it that. The forecasters are calling it, in plain terms in the public discussions you can pull up right now on the National Weather Service website, conditions that produce major wildfire events. You have to understand something about fire weather meteorologists. They write in a deliberately understated voice. When they say any fires that develop will have the potential to spread rapidly, that is the operational flaw of their concern language. When they say fires will catch and spread quickly, they have moved up one level. When they say damaging winds will blow down trees and power lines, widespread power outages are expected, they have moved up another level. The Mojave Desert Slopes warning today says exactly those words. The National Weather Service Hanford language for the Westside Hills today says, and I'm quoting from the morning text, that the highest threat is fast-moving grass fires under these conditions. That phrase, fast-moving grass fires, is the operational signal that a National Weather Service office is communicating that the fuel and wind combination will produce fire spread rates faster than firefighters can respond to. In an internal calculation, with single-digit humidity and gusts in the 30s to 70s, fire spread rates in cured grass can exceed 2 miles per hour under sustained conditions. With gusts factored in, the gust front advance can briefly exceed 4 miles per hour. That is a sustained jog. That is the speed at which a wildfire moves through this kind of fuel that is sitting on the floor of the Sacramento Valley right now. The ignition probability under these conditions is the part that quietly changes everything. The phrase ignition probability sounds like a technical detail, but it is the key number. In normal fire weather conditions, the probability that a single spark dropped on the ground will start a fire that propagates beyond its initial half-meter circle is in the range of single-digit percentages. Most sparks do not start fires. The fuel bed needs a specific combination of moisture content, wind, and ambient temperature to take ignition. Under today's conditions across the red flag corridor, the ignition probability from a single spark approaches 100%. That is not an exaggeration. That is the operational number that fire behavior models output when relative humidity is in the single digits. Fuel moisture content in the 1-hour class is below 2%, and ambient temperatures are in the 80s or 90s. Every spark starts a fire today. Now layer on the natural ignition source. The Storm Prediction Center, in its Day 1 fire weather outlook valid for today, has 3 risk categories simultaneously active. The first is elevated wind and humidity risk, which covers a broad area of the western United States. The second is critical wind and humidity risk, which is the upgraded category that covers the highest risk core of the corridor. The third, which is the one that makes today operationally different from a normal red flag day, is the isolated dry thunderstorm risk. A dry thunderstorm is a thunderstorm that produces cloud-to-ground lightning, but whose precipitation evaporates before reaching the surface. The thunderstorm produces an ignition mechanism, lightning, but it does not produce the rainfall that would normally suppress that ignition. Dry thunderstorms are the single most operationally feared natural ignition source in modern Western fire weather because they distribute lightning strikes across geography that is otherwise unreachable for human-caused ignitions, and they place those strikes on top of fuel that has no surface moisture to fight back with. To put the dry lightning ignition source into historical context, consider the August Complex fire of 2020 in Northern California. The August Complex was the single largest fire in California history. It just barely exceeded 1 million acres of burned area. Its ignition cluster is one of the most studied in modern wildfire science. Approximately 50% of the ignitions in the August Complex cluster were traced to a single dry lightning outbreak that occurred between August 16th and August 17th, 2020. One lightning outbreak on one terrain under one fire weather regime started the fires that became the largest fire in the history of California. That is the consequence of dry lightning on the ground under conditions like today's. The Storm Prediction Center is currently telling you, in the Morning Outlook, that today's regime includes an isolated risk of exactly that ignition source, geographically co-located with the dry corridor. And then there is the second ignition channel, which the operational discussions reference more obliquely. The Storm Prediction Center's Day 1 convective outlook places an enhanced risk of severe thunderstorms across the central high plains for the same afternoon. The enhanced risk box explicitly calls for wind gusts of 75 miles per hour or higher, hail of 2 inches or larger, and a few tornadoes possible. The Day 2 outlook upgrades the central plains into a corridor that runs from central Nebraska through southwest Minnesota, with supercells, very large hail, and tornadoes expected on Sunday. That severe thunderstorm corridor is partially overlapping with the eastern edge of the fire weather corridor in the Texas and Oklahoma Panhandle, so you have, on the same afternoon, on the same continent, a continuous corridor of fire weather conditions that runs from the Sierra to the Texas Panhandle, with a co-located severe thunderstorm corridor on its eastern edge that is statistically guaranteed to produce cloud-to-ground lightning. Whether or not those lightning strikes hit dry fuel will be determined in the next 72 hours by where exactly the storm tracks travel and where exactly the boundary between moist Gulf of Mexico air and the dry continental air sits. But the ignition mechanism, the natural ignition source for a megafire class event, is on the field today. And here is the part that, when you start to assemble it, becomes the story. Every single megafire in modern American history started under conditions less severe than what is operationally active right now across 6 states. The Camp Fire in Paradise, the Tubbs Fire in Wine Country, the Marshall Fire in Boulder County, the Smokehouse Creek Fire in the Texas Panhandle, the Carr Fire in Redding, the August Complex in Northern California. Every one of those events was ignited under wind and humidity conditions that today's regime meets or exceeds. The conditions are not the events. A fire requires an ignition, and the ignition is stochastic. Whether or not an ignition occurs in any specific hour depends on factors no forecast can fully predict. A piece of farm equipment, a worn power line, a dropped cigarette, a stochastic lightning strike. But the strongest historical pattern, the one that the operational fire weather community keeps in its institutional memory, is this. When the wind, the humidity, the fuel, and the atmospheric instability all reach the regime that is active right now, the question is not whether an ignition will occur somewhere in the corridor. The question is when, and where, and what gets in the path of the fire after it does. The forecast extends through Monday. The drought underneath it extends through summer. The Mojave slopes will see gusts in the high 60s and low 70s through tomorrow night. The Texas Panhandle will see 4% humidity again on Sunday. The Sacramento Valley will see overnight humidity recovery that is too low to refresh the fuel bed before the next afternoon's dry down starts. The dry corridor opened this morning, It does not close until at least Monday night. Somewhere in that 72-hour window, on some ridge or canyon or piece of highway right-of-way or piece of power line corridor inside the warning footprint, a spark is going to find a way onto dry fuel under 30-mile-per-hour wind. That is what the operational meteorologists know, and that is why the morning discussions, the ones you can read for yourself on the National Weather Service website, are using the deliberately understated language that they always use, but pointing it at the conditions that produced every megafire in modern American history. Think for a moment about what a red flag warning actually represents in operational terms. The National Weather Service does not issue a red flag warning lightly. The criteria are explicit, the thresholds are validated against historical fire outcome data, and the issuance itself triggers a cascade of operational responses across the federal and state fire management agencies. When a red flag goes up, the local Bureau of Land Management office adjusts its prescribed burn schedule. The US Forest Service repositions its initial attack resources. State emergency management agencies update their staffing levels. Insurance companies and electrical utilities monitor the alert in real time. The red flag is not a public information bulletin. It is a coordinated operational instruction that the warning area has crossed into a regime where any ignition will likely escape initial attack. When 26 of those warnings are issued at the same time across 6 states, the operational footprint of the response is continental in scale. There are not enough initial attack crews in the western United States to put a rapid response presence into every county under warning today. The fire management agencies know this. They have known it for weeks. The pre-positioning of crews has been happening since the May 9th corridor in the Northern Plains. The current corridor is the activation of the resources that the operational community has been quietly preparing for since the spring. The storm prediction centers fire. Weather Outlook deserves a closer look because the structure of the outlook itself tells you something about how the operational forecast community is thinking about today. The outlook is organized into categories that scale with the operational severity of the fire weather risk. Elevated is the lowest tier, indicating that conditions are conducive to enhanced fire behavior, but not necessarily to extreme behavior. Critical is the next tier, indicating that wind and humidity have reached levels that historically produce significant fire growth. Isolated dry thunderstorm is a separate category that flags the natural lightning ignition risk. A fourth category, extreme, is reserved for the absolute upper tail of the operational distribution and is issued only a handful of times per year in the modern record. Today's outlook is at the critical tier with the isolated dry thunderstorm overlay. The combination, on a single afternoon, across the geographic footprint that today's outlook covers, is the maximum operational designation short of an extreme day. The operational fire weather community has, in plain terms, declared today the upper edge of what it can flag without going to the highest tier on the rating system. What makes this even more structurally unusual is the way the warning corridor connects with the severe weather corridor on its eastern flank. The Storm Prediction Center's Day 1 convective outlook places an enhanced risk of severe thunderstorms across the central high plains, with explicit language about wind gusts of 75 miles per hour or higher, hail of 2 inches or larger, and a few tornadoes possible. That severe weather corridor sits immediately east of the easternmost red flag warning in the Texas and Oklahoma Panhandle. The two corridors are not on opposite sides of the continent. They are touching. The boundary between them is the operational dry line that separates moist Gulf of Mexico air to the east from dry continental air to the west. The dry line is the focus for the severe thunderstorm activity, and it is also the focus for cloud-to-ground lightning. If a thunderstorm produces lightning that crosses the dry line westward into the red flag corridor, it lands on dry fuel. Whether that crossover happens and where is not something the morning forecast can specify with precision. It depends on the moment-to-moment evolution of individual storm cells through the afternoon. The operational possibility is on the table. The natural ignition source could deliver itself onto the dry corridor by tomorrow night. So the question that lands at the end of all of this is the question that doesn't have an answer yet. We know what conditions produce megafires. The conditions are active. The corridor is open. The drought underneath it is the worst on the modern observational record. The fire season has not officially started yet. So if this is the trigger and the drought is the loaded gun, what is the bullet and where is it heading? Part 2. How the drought built the gun. 3 days ago, the video on this channel covered what is, as of this week, measurably and verifiably the worst drought in the modern observational record of the United States. Not the worst in a region, not the worst for a category, the worst on a national, integrated, instrumental record that the National Centers for Environmental Information has maintained since the late 19th century. The video on the worst drought in US history put 112,000 viewers in front of the data, and the data is structurally what today's fire weather corridor sits on top of. To understand what is happening in the Sierra and the Mojave and the Texas Panhandle today, you have to understand the soil column, the snowpack, the live fuel moisture, and the megadrought baseline that this dry air event arrived on top of. The US Drought Monitor is the weekly map you would have seen referenced in the May 13th video. It is produced jointly by the National Drought Mitigation Center at the University of Nebraska, the US Department of Agriculture, and the National Oceanic and Atmospheric Administration. The monitor classifies every county-level area of the United States into one of 5 categories, ranging from D0, which is abnormally dry, but not yet in drought, through D1 moderate, D2 severe, D3 extreme, and finally D4 exceptional, which is the highest classification on the map. As of the most recent weekly release, the central, southern, and eastern United States are running a footprint of D3 extreme and D4 exceptional drought that the Drought Monitor record has not previously shown for this geography in this season. The Southern Plains Corridor, which is the eastern edge of today's fire weather warning footprint, is anchored in D3 extreme drought, with portions of the Texas Panhandle, the Oklahoma Panhandle, southwest Kansas, and the New Mexico-Texas border zone all running D3 or worse. The southeastern United States, which historically does not experience this category of drought except in compounded multi-year events, is approaching D4 exceptional in Florida and the southeast Atlantic coastal strip. The map looks like a continent-scale version of a dry sponge. The Southern Plains Corridor is the part of that sponge that overlaps geographically with the fire weather corridor active today. The Integrated Palmer Drought Severity Index, which is a different metric than the Drought Monitor, and which is computed by the National Centers for Environmental Information across a 131-year record extending back to 1895, came in for March of this year at negative 7.85. April came in at negative 7.56. To understand what those numbers mean, you have to understand the historical reference frame. The Dust Bowl peak in July of 1934 was negative 8.09. In August of 1934 it was negative 8.42, so the spring of 2026 is sitting within 1/10 of 1 unit of the Dust Bowl peak, on a continental scale integrated metric, for a season that climatologically should still be wet. That is not a comparison made to alarm. That is a numerical observation. The instrument is reading values that the instrument has only seen in its history during the single most catastrophic agricultural drought event of the 20th century. The eastern half of the United States, which historically operates under different drought dynamics than the western half, is showing a southeastern flash drought signature that the regional climate science community has been studying with increasing concern for the past decade. The southeast climate region recorded its driest April in approximately 40 years. 6 Atlantic coastal states ranked their April at 2026 in the top 10 driest Aprils on the local record. Florida ran approximately 99% of its land area under some category of drought during the April peak, and it is now running approximately 78% in D3 extreme and 22% in D4 exceptional. The Florida drought is the most intense 15-year stretch on the modern Florida observational record. The southeast aggregate is running approximately 99% under drought, with 61.5% in D3 or D4. These are not statistics that fit a single bad month. These are statistics that fit a multi-month structural shift in the precipitation regime. The western half of the United States operates under a different drought clock, anchored in winter snowpack. The Sierra Nevada, the Cascade Range, the Northern Rockies, the Wasatch, the San Juans, and the Colorado Rockies all build their water year reservoir through October to April snowfall, which then melts through the spring and summer to feed rivers, reservoirs, and groundwater. The water year 2025 to 2026 saw 8 western states post snow water equivalent values, the standard metric the Natural Resources Conservation Service uses, at or near record low levels on April 1st. Arizona, Colorado, Idaho, Nevada, New Mexico, Oregon, Utah, and Wyoming were all carrying snow water equivalent values below the 10th percentile of the modern record at the spring measurement point. California ran the second lowest snow water equivalent on the SNOWTEL record. Oregon recorded 2.1 inches of snow water equivalent on April 1st, which is 12% of the 1981 to 2010 median, the lowest April 1st snow water equivalent on the Oregon record. The structural problem with low snowpack is not just that it reduces total water availability through the summer, it is that it removes the seasonal bridge that historically separates spring fuel, curing from the start of fire weather season. In a normal year, the snowpack at high elevation continues melting through April, May and early June, releasing cold water into the streams and the soil column, maintaining humidity in the riparian zones, holding fuel moisture above critical thresholds in the chaparral and the conifer understory. In a low snowpack year, that bridge collapses. The dry down accelerates. The fuel curing that historically completes by mid-June completes by mid-May. The high elevation fire weather window, which historically opens in late June or July, opens in May. That is the structural mechanism that the May 16th red flag corridor is operating inside of. The Colorado River Basin, which is the integrated water resource for approximately 40 million people across 7 western states, recorded its warmest March on the basin's instrumented record at 13.7 degrees Fahrenheit, above normal across the upper basin. Lake Mead is currently at 1,055 feet of elevation, which is approximately 30% of full capacity. Lake Powell is at 3,526 feet, approximately 23% of full capacity. The minimum power pool elevation for Lake Powell is 3,490 feet. If Lake Powell drops below that elevation, Glen Canyon Dam can no longer generate hydroelectric power, and the operational management of the entire downstream Colorado River system enters territory it has never been in. Current trajectory models place that risk in the late 2026 to early 2027 window. The reason this matters for a fire weather video is that the Colorado River system is the integrated indicator of what is happening to the entire western water cycle. When Lake Mead is at 30% and Lake Powell is at 23%, the soil column across the basin is empty, the vegetation is stressed, and the fuel matrix is biologically pre-staged for fire. The Ogallala Aquifer, the massive freshwater reservoir under the Texas, Oklahoma, Kansas, Nebraska, and South Dakota High Plains, declined at a rate of approximately 0.66 feet during the 2025 water year. Approximately 40% of the aquifer is now considered unusable on an 80-year horizon. The depletion across the period 2001 to 2011 alone accounted for approximately 1/3 of the entire 20th century depletion of the aquifer. The aquifer is sitting underneath the Texas and Oklahoma Panhandle that is currently under the worst red flag conditions in the corridor. The vegetation in dryland farms across the Panhandle, which is rooted into soils that are no longer being recharged from below, is curing earlier and more aggressively than in any prior comparable May. The deepest scientific framing for what the West is experiencing comes from a series of papers published over the past decade by researchers, including Park Williams, Benjamin Cook, and Jason Smerdon at the Lamont Doherty Earth Observatory, and collaborators across the Western climate science community. The single most cited paper in this group is Williams, Cook, and Smerdon, published in 2022 in Nature Climate Change, titled Rapid Intensification of the Emerging Southwestern North American Megadrought in 2020 to 2021. The paper extended an earlier 2020 Williams paper in Science by reconstructing soil moisture across the southwestern United States using tree ring records extending back roughly 1,200 years. The conclusion of the paper, and the conclusion that has been referenced repeatedly in this channel's drought coverage, is that the period from 2000 to 2021 was the driest 22-year stretch in the southwestern United States in at least 1,200 years. The paper attributed approximately 42% of the observed soil moisture deficit across that 22-year window to anthropogenic warming, with the remainder attributable to natural variability. A follow-up CU Boulder analysis published in 2025 updated the attribution with additional data, and the framework remains the dominant scientific reference point for understanding why Western US droughts in the modern era are operationally different than droughts of the early 20th century. The megadrought baseline matters for today's fire weather corridor in a specific operational way. In a normal precipitation regime, a single dry month, even a record dry single month, does not produce the fuel state we are seeing today. The fuel matrix has reserves, the soil column has reserves, the aquifer groundwater has reserves. A single dry month can extend the curing process by a few weeks, but the underlying biological hydration is still there. Under mega-drought baseline conditions, those reserves are gone. The soil column is operating below its functional moisture floor across multi-year integrations. The aquifer groundwater has been pulled down. The fuel matrix is curing not from a fully hydrated starting point, but from a baseline that is already dry. So when you put a dry month, or a heat dome, or a wind event on top of mega-drought baseline conditions, the system does not respond linearly, it responds with multiplication. A single bad month under mega-drought is operationally not a single bad month. It is the trigger of a fully cured fuel matrix months early. The agricultural impact is the other half of the drought signal, and it is the half that connects to the question of whether the mega-drought baseline is going to recover this year. The US Department of Agriculture's 2026 wheat acreage report posted total seeded acres at 43.8 million, which is the lowest US wheat acreage figure since 1919. That is not a statistic about climate. That is a statistic about which farmers, looking at the soil moisture map and the regional precipitation outlooks, decided not to plant. Of the seeded acres, the May 2026 crop progress report had US winter wheat at approximately 30% good to excellent, the lowest figure for this point in the season in approximately a decade. 69% of the US wheat growing area was in some category of drought, including 95% of the southern plains, where today's fire weather warnings are most intense. Kansas reported 78% of its winter wheat as very poor, poor or fair. Oklahoma reported nearly half of its winter wheat in the very poor or poor categories. The Kansas State University production model projected a 31% reduction in production, totaling roughly 240 million bushels of lost output relative to a normal year. The cattle herd is reading the same signal. The US beef cow herd is at 27.6 million head, the lowest level since the early 1950s. The total cattle inventory is at approximately 86.2 million head, a 74-year low. Approximately 60% of the US cattle herd is in drought-affected counties. The USDA is forecasting record beef prices through 2026. No meaningful herd expansion is projected until 2028 at the earliest. The reason this matters for the fire weather story is the same reason the wheat acreage matters. The agricultural sector is reading the soil moisture map, the precipitation outlooks, and the multi-year baseline, and it is responding by reducing the agricultural footprint across the drought-affected geography. That reduced footprint is, paradoxically, increasing the fire risk in some areas because abandoned fields cure into pure fine fuel without management, and managed grazing, which historically reduces fuel loading in grassland systems, is being pulled back across millions of acres. The integrated message from the drought layer is this: the May 16th fire weather corridor is not arriving on top of a normal precipitation baseline that happens to have hit a bad month. It is arriving on top of a 22-year mega-drought, layered on top of a winter that produced record-low snowpack across 8 western states, layered on top of a spring that ran the worst integrated Palmer drought index reading the lower 48 as seen in approximately 90 years. The drought built the fuel. The drought emptied the soil column. The drought collapsed the snowpack bridge. The drought is the gun. Today is the trigger. And the part that the May 13th video framed but did not fully resolve is the question of whether the drought is going to break. The current ENSO state is neutral and trending warm. The current Pacific North American teleconnection pattern is in a configuration that historically delivers below normal precipitation to the southwestern United States. The current jet stream geography is locked in a Rossby wave configuration that has persisted for multiple weeks. None of these conditions are projecting a meaningful precipitation recovery for the affected geography in the next 30 days. The National Interagency Fire Center's 2-year predictive services outlook projects above normal significant fire potential across most of the western United States for June, July and August of 2026. That outlook was published before today's red flag corridor activated. The outlook stands today. The fire season is not expected to be easier than today's regime. It is expected to be the multi-month version of today's regime. There is one more dimension to the drought layer that the May 13th video alluded to, but did not fully unpack, and it has to do with the way drought conditions change the structural availability of fuel for fire over the medium term. In a normal fire weather year, The fuel that is available to burn is the fuel that has cured to the operational moisture threshold for ignition. Some species of vegetation cure earlier in the season than others. Annual grasses cure first, fine deadwood second, then chaparral and brush species, and finally the conifer understory and live tree canopy. The historical fire weather window opens as each fuel type cures, and the window for any given fuel type is bounded on the front end by the curing date and on the back end by the first significant precipitation event that rehydrates the fuel below the ignition threshold. Under mega-drought baseline conditions, the bookends of those windows change. The front-end curing dates move earlier. The back-end rehydration events become rarer and weaker. The window for each fuel type widens, and the integrated period during which all fuel types are simultaneously available, which historically is a relatively short window in late summer, expands into a multi-month period that can stretch from late spring through fall. The fuel availability profile of the mega-drought era is structurally different from the fuel availability profile of the pre-mega-drought era. The window of total fuel availability is wider. The window in which all the cured fuel categories are operationally ignitable is longer. And the operational consequence is that the climatological fire weather season is not just shifted earlier. It is also extended later. The window is wider on both ends. The Florida case is worth pausing on as a separate sub-narrative because Florida is operationally different from the Western fire weather geography, but is currently in a structural state that is unprecedented in the modern Florida record. Florida's fire weather risk is anchored in the peat fuel matrix of the Everglades and the cypress swamps of the central and southern peninsula. Peat fuel is structurally different from grass or chaparral fuel because peat is below-ground organic material that, when sufficiently dry, can support a smouldering combustion process that propagates underground at very low rates of spread but is essentially impossible to extinguish through standard suppression methods. The Indonesian peat fires of 1997, which were tied to a strong El Niño event, released between 0.8 and 2.57 gigatons of carbon, representing approximately 13 to 40% of global fossil fuel emissions for that year. Florida's Everglades peat system is geographically smaller than the Indonesian system, but is structurally similar in its combustion behavior. The Florida fire of 1998, which followed a previous El Niño-driven drought period, burned approximately 500,000 acres and produced the largest peacetime evacuation in Florida history. The current 98% drought coverage of Florida, with 78% in D3 and 22% in D4, is the preconditioned state for a peat fire scenario that has not been operationally observed in the modern era. The May 11th coverage on this channel covered the Max Road Miramar fire in the Everglades, which had burned approximately 4,800 acres in the early stages of what may become a much larger Florida fire season. The Florida fire risk is, in structural terms, parallel to the Western fire weather risk we are covering today, and it is being driven by the same mega-drought baseline plus the same anomalously warm spring. The loaded gun is not just loaded, it is loaded for months. And the chamber is not just one round, it is multiple rounds in multiple geographies, simultaneously cocked, simultaneously aimed. Part 3. Vapor Pressure Deficit, the silent driver no one talks about. There is a metric in fire science that almost nobody outside the field knows about, and it is doing more analytical work in modern wildfire research than any other single variable. It is called vapor pressure deficit. The phrase sounds technical, and it is, but the underlying concept is something every person who has ever stepped outside on a hot, dry day already understands intuitively. Vapor pressure deficit is the atmosphere's thirst. It is the measure of how aggressively the air is pulling moisture out of every surface it touches, including the leaves of every living plant, the bark of every tree, the litter on every forest floor. The higher the vapor pressure deficit, the faster the moisture is being pulled out, and when the vapor pressure deficit reaches the values that are being recorded across the western United States this afternoon, the air is pulling moisture out of vegetation faster than the precipitation regime, the soil column, and the biological process of root water uptake can possibly replace it. The physics of vapor pressure deficit is anchored in a relationship called the Clausius-Clapeyron equation, which is a mid-19th century thermodynamic result that quietly governs an enormous amount of what happens in the modern climate system. The equation tells you that the maximum amount of water that can be held in a parcel of air before that water condenses out as a cloud or a fog or precipitation increases non-linearly with temperature. The standard approximation that climate scientists use is that for every 1 degree Celsius increase in air temperature, the maximum water holding capacity of the air increases by approximately 7%. That is the Clausius-Clapeyron rate. It is one of the deepest physical constants underlying the operational climate response we are currently living through, and it is the reason that the same volume of dry continental air becomes structurally more dangerous as the air warms. The vapor pressure deficit, then, is the gap between the saturation level of the air at its current temperature and the actual amount of water currently in the air. When the air is warmer, the saturation level goes up. If the absolute moisture content of the air does not go up at the same time, the gap widens. The gap is the deficit, and the deficit is what determines how aggressively the air pulls moisture out of any surface it touches. Now apply this to the conditions across the western United States right now. The Texas and Oklahoma Panhandle is sitting at 4% relative humidity at temperatures in the mid-90s to low 100s. That combination, in absolute vapor pressure deficit terms, is at the upper edge of any operational reading the National Weather Service has ever recorded for that geography in May. The Mojave Desert is at 10% relative humidity in temperatures in the upper 80s. The Sacramento Valley is at 7 to 15% humidity and temperatures in the low to mid-80s. Every one of these regions is operating with a vapor pressure deficit that, in classical fire behavior modeling, sits in the territory that historical megafires required for their most rapid spread phases. The air is pulling moisture out of every surface, and the surfaces, the vegetation, the litter, the soil, have nothing left to give. The single most important academic paper on the role of vapor pressure deficit in modern wildfire was published in 2019 in the journal Earth's Future by a team led by Park Williams and John Abatsoglu, titled Observed Impacts of Anthropogenic Climate Change on Wildfire in California. The paper analysed approximately 50 years of California fire records from 1972 through 2018 and decomposed the dramatic increase in California's summertime burned area across that period into the variables that mathematically explained it: population growth, ignition sources, land management practices, fuel load changes. All of those entered the model. But the dominant single explanatory variable, the variable that did the most work in the regression, was the vapor pressure deficit trend. The paper concluded that approximately half of the observed doubling of California's summertime burned area across the 1972 to 2018 window was directly attributable to the vapor pressure deficit increase alone. Half, not climate change in general, not warming temperatures in general. Specifically, the increase in the atmospheric thirst, measured as vapor pressure deficit, was responsible for roughly half of the doubling of how much California burned every summer. The reason this paper matters for understanding today's regime is that the vapor pressure deficit increase over the period the paper studied was approximately 50% over baseline. So the air, over the warm season, became about half again as aggressive at pulling moisture out of vegetation as it had been at the start of the period, and the result, in burned area terms, was a doubling of how much terrain burned every summer. Now project that finding onto a day where the vapor pressure deficit is, in absolute terms, sitting at the upper edge of the operational distribution for May. Today's deficit values across the corridor are not at the average of the modern era. They're at the tail, and the tail is where the megafire events live. A second foundational paper, also in this same scientific lineage, was published in 2016 in the Proceedings of the National Academy of Sciences by John Abatsoglu and Park Williams, titled Impact of Anthropogenic Climate Change on Wildfire Across Western US Forests. This is the paper that, in the federal land management community and in the operational fire weather meteorology community, is the single most cited reference work for the climate-wildfire connection. The paper analysed forest fire records across the entire western United States from 1979 to 2015 and concluded that approximately 55% of the observed increase in fuel aridity across western US forests since 1979 was directly attributable to anthropogenic warming. The paper further concluded that anthropogenic climate change had approximately doubled the cumulative forest fire area across the western United States in the 1984 to 2015 window, compared to a counterfactual world without that warming. That paper is the reason that the National Interagency Fire Center, the US Forest Service, the Bureau of Land Management, and the Intergovernmental Panel on Climate Change all operationally state that wildfire risk in the western United States has measurably and structurally increased as a consequence of warming. It is not a controversial scientific finding. It is one of the most replicated and well-supported attribution results in the modern climate science literature. A third paper, published in 2015 in Nature Communications by a team led by W. Matt Jolly at the US Forest Service Rocky Mountain Research Station, titled Climate-Induced Variations in Global Wildfire Danger from 1979 to 2013, took the analysis to a global scale. The paper found that, across the planet, the fire weather season length had increased by approximately 19% from 1979 to 2013. The increase was not uniform. Some regions saw larger expansions, others smaller, but the global mean was an additional approximately 1/5 of the calendar year now operating under fire weather conditions compared to the late 1970s. For North America specifically, the expansion was approximately 4 weeks. The fire weather window of the modern era is about a month longer on average than the fire weather window of 40 years ago. If you take those three papers together, Jolly 2015 on the global season length expansion, Abatzaglo and Williams 2016 on the fuel aridity attribution, and Williams and Abatzaglo 2019 on the vapor pressure deficit driver, you arrive at a coherent scientific picture of why today's regime is happening on May 16th instead of late June. The fire weather season has expanded into a window it did not historically occupy. The expansion is structural, not stochastic. The expansion is attributable to warming, with high statistical confidence. The mechanism is the vapor pressure deficit, and the today-specific consequence is that, on May 16th in 2026, the operational fire weather corridor across 6 western states is exactly the kind of corridor the science predicted would become normal in this expanded season. There is a more subtle layer to the vapor pressure deficit story that is worth pausing on, because it explains why the warming equals more fire relationship is not a simple linear scaling. The relationship is amplified by the Clausius-Clapeyron nonlinearity. Every additional 1 degree of warming does not just add 1 degree of fuel aridity, it compounds the saturation deficit. So a 1 degree warming above the early 20th century baseline produces a noticeably larger increase in vapor pressure deficit than the temperature change alone would suggest. A 2 degree warming produces a more than twice as large increase. A 3 degree warming produces a substantially larger increase still. This is why the climate attribution research community has come to focus on vapor pressure deficit as the operational explanation for why the wildfire response to warming has been faster than the temperature response. The atmosphere is thirstier than the temperature alone would predict. The honest scientific position on what the vapor pressure deficit framework means for today is that we are operating in a regime that the historical fire behavior models, the ones the federal agencies still use for tactical fire suppression decisions, were not fully calibrated against. The models were built on observations from the 1980s, the 1990s, and the early 2000s. The vapor pressure deficit values that the models treated as outlier upper tail events are now, in years like this one, the operating values during the fire weather peak. The models are being updated. The operational community has been updating them year by year. But the lag is real. Today's fire behavior modeling is, in many respects, an extrapolation beyond the training data that originally informed the models. This is why, when you listen to operational fire weather meteorologists in interviews, the kind of interviews where they speak somewhat freely about what they actually see in their data, they consistently mention that the conditions they are seeing in recent years are not the conditions they were trained against. The 4% humidity in the Texas Panhandle today is not anomalous because it has never happened before. It is anomalous because the cumulative frequency of 4% humidity days across the modern record has increased measurably year over year. The 70-mile-per-hour gust on the Mojave Desert Slopes is not anomalous because the Mojave has never seen 70-mile-per-hour gusts. It is anomalous because the simultaneous occurrence of 70-mile-per-hour gusts with sub-20% humidity on a 90th percentile fuel bed 3 weeks before climatological fire season onset is occurring more often than it did a generation ago. The corridor is wider, the window is longer, the atmosphere is thirstier. Now, this is where the scientific framework starts to feel relevant to the human-scale question of what to actually do. The vapor pressure deficit increase is not something any single individual can directly reduce. It is a continental scale, global scale, multi-decade physical process driven by the underlying temperature increase. But the consequences of that increase, in fire risk specifically, are something the operational and emergency management communities have been quietly preparing for. the expanded NIFC Predictive Services Outlook, the year-round readiness language now embedded in US Forest Service and Bureau of Land Management staffing protocols, the structural shift in wildland firefighter deployment patterns to maintain a larger off-season ready force, the increasing investment in fuel treatment programs and prescribed burn programs, all of these are responses to the fact that the fire weather window has expanded and that the windows of safe ignition vector reduction have correspondingly compressed. The thing the broader public has not yet fully metabolized is that the expanded fire weather window does not just affect the western United States in summer, it is now reaching into the spring shoulder season, and in years like this one, with mega drought baseline conditions, the spring shoulder season is producing fire weather corridors that operationally match peak summer. The fire weather corridor across 6 states today is the operational verification of approximately a decade of climate attribution work that predicted exactly this. The science was not silent about it. The science said this would happen. The science said the fire weather season would expand. The vapor pressure deficit framework gave us the mechanism. The Williams and Abatsaglu papers gave us the attribution. The Jolly paper gave us the global confirmation. The papers were published. The papers were peer-reviewed. The papers were ignored by most of the audience the science was trying to reach. And the consequence of that lag is that, when the conditions arrive, the public response is the surprise of someone seeing the consequence of a forecast they did not know existed. This is the silent driver, the vapor pressure deficit, the atmosphere's thirst, the Clausius-Clapeyron nonlinearity, the mechanism behind every megafire of the past decade, the reason today is happening in May instead of July, the reason the corridor stretches from the Sierra to the Texas Panhandle, the reason the conditions are operationally indistinguishable from peak summer. The science has been telling us this was coming. The conditions are here. The corridor is open. And the next question is the one we have to ask if we're going to take the science seriously. What does the historical record show happens in the specific kind of fire weather regime that is active right now? Part 4. The fingerprint of every megafire, from Camp Fire to Smokehouse Creek. The reason today's regime feels different is because the historical record gives us a very specific reference class for what happens when the wind, the humidity, the fuel, and the atmospheric configuration look like what is operationally active right now. Every modern American megafire that has produced significant loss of life, significant loss of homes, or significant economic damage has been ignited under conditions that are, in operational terms, the same regime, or a less severe version of the regime that is on the field today. The reference class is not theoretical, it is not extrapolation, it is the empirical record of the past decade, and it tells you exactly what kind of consequence the active regime is capable of producing. The case study that anchors the modern reference class is the Camp Fire, which ignited on the morning of November 8, 2018, near the town of Paradise, California, in the Sierra Nevada foothills of Butte County. The Camp Fire killed 85 people. It destroyed 18,804 structures. It is, by any measure of human cost, the most catastrophic single wildfire in modern American history. And the operational conditions on the morning of November 8, 2018, are the operational reference point you need to understand what kind of regime today is. On the morning of November 8th, the National Weather Service had issued a red flag warning for the area surrounding Paradise. The forecast was for east-northeast winds of 15 to 30 miles per hour, with gusts in the high 50s and low 60s miles per hour. The relative humidity was forecast in the range of 10 to 15%. The ambient temperature was forecast in the mid to upper 60s. The fuel matrix in the Sierra Nevada foothills was, by mid-November standards, fully cured. The chaparral, the oak woodland, and the conifer understory were carrying late-season moisture levels in the low side of their normal autumn range. The atmospheric column above the area was carrying a Diablo wind configuration, which is the Northern California version of the dry-down slope offshore flow regime that periodically descends out of the Great Basin and across the Sierra in autumn. The Diablo configuration is anchored in a pressure gradient between an inland high-pressure system, sitting over the high desert of the Great Basin, and a low-pressure trough offshore. Air flowing from the high to the low descends across the Sierra crest, compresses adiabatically as it loses elevation, and warms approximately 1 degree Celsius for every 100 meters of descent. The temperature rise without water addition produces a corresponding collapse of relative humidity into the single digits. The ignition of the campfire occurred at approximately 6:30 in the morning at a transmission tower owned by Pacific Gas and Electric in the Feather River Canyon. The legal and forensic investigation concluded that the ignition was caused by a failure in a 100-year-old high-voltage transmission line, specifically the failure of a worn metal hook called a C-hook that supported one of the conductors. The wear on the C-hook had reduced its structural margin to the point that, under wind loading, it failed. The conductor fell. The fall produced an electrical arc. The arc ignited the dry vegetation underneath the tower. Within minutes, the fire had escaped initial attack capability. Within an hour, it had spotted across multiple drainage divides through embercast. Embercast is the phenomenon in which a wildfire under high wind conditions throws burning fragments of fuel, pieces of bark, leaf, twig, structure, downwind of the fire front. Under 60-mile-per-hour wind, embercast can carry burning fragments more than a mile ahead of the fire front. Those fragments land on whatever fuel is in the path, nearby vegetation, structures, vehicles, roadside debris, and produce secondary ignitions. In a high-wind, low-humidity cured fuel regime, embercast is the mechanism that allows a wildfire to behave like a moving wave rather than a single-front advancing line. The campfire's progress into the town of Paradise was driven primarily by embercast. Structures ignited not because the fire front reached them, but because burning fragments landed on roofs and decks miles ahead of the advancing flame front. The reason the campfire reference matters for understanding today's regime is the operational comparison. The Mojave Desert Slopes today are forecast for gusts to 70 miles per hour, which exceeds the gust that the campfire ignited under. The Sacramento Valley today is forecast for gusts to 50 miles per hour, which is in the same range. The relative humidity in the Sacramento Valley today is forecast at 7 to 15%, which is comparable to or drier than the campfire conditions. The fuel state in the Sacramento Valley today, with the mega-drought baseline and the early cured live fuel moisture content, is at least as dry as the campfire fuel state in November. The atmospheric configuration today is a structurally analogous downslope wind regime, driven by the same kind of pressure gradient mechanism that produced the campfire's Diablo wind, scaled up to a deepening upper trough across the Intermountain West. Move backward 1 year to October 8, 2017. The Tubbs Fire ignited in Sonoma County, California. The Tubbs Fire killed 22 people and destroyed approximately 5,600 structures, including significant portions of the city of Santa Rosa. The ignition conditions were almost identical to the campfire pattern that would follow a year later, a Diablo wind event with gusts in the 50 to 70 mile per hour range, relative humidity in the single digits, and cured fuel in the chaparral and oak woodland ecosystems of the wine country foothills. The ignition source was, again, electrical infrastructure, although the specific cause was a private electrical fault rather than a transmission line failure. The fire's progression into Santa Rosa was driven primarily by embercast. The structures that burned in the Coffee Park neighborhood, in the urban core of Santa Rosa, miles from any wildland fuel, were ignited by embers carried on the wind from the wildland-urban interface. The Tubbs Fire is, in the modern reference class, the proof of concept for the urban fire spread mechanism, the demonstration that, under high wind, low humidity, cured fuel conditions, a wildfire can transition from a wildland fire to an urban conflagration that propagates through structures rather than through vegetation. The Marshall Fire, which ignited on December 30, 2021 in Boulder County, Colorado, is the case study that operationally rewrote the National Weather Service's red flag threshold criteria for the Boulder office. The Marshall Fire destroyed 1,084 homes and killed 2 people. The wind on the day of the fire was extraordinary. Peak gusts recorded at 115 miles per hour at the Arvada station, 110 miles per hour at Rocky Flats, and 103 miles per hour at the White Ranch station. The relative humidity on the day of the fire was in the range of 20 to 25%. The fuel matrix had been pre-cured by an unusually dry autumn following a record warm summer. The Marshall Fire's most operationally important detail, the one that the National Weather Service Boulder office subsequently rebuilt its threshold language around, is that no red flag warning had been issued. The relative humidity at the time of ignition was 20 to 25%, and the then active National Weather Service Boulder red flag warning threshold required 15% humidity. The fire occurred under conditions that exceeded the operational warning threshold of the day. After the Marshall Fire, the Boulder office revised its threshold criteria to incorporate the wind state as a cofactor with humidity, recognizing that 100-mile-per-hour gusts on 20% humidity fuel produced fire behavior that exceeded the original humidity-only threshold model. Today's Mojave Desert Slopes warning, with gusts to 70 and humidity at 10 to 20%, sits inside the post-Marshall revised criteria with significant margin. The threshold revision is operationally what allowed today's warning to be issued under the new framework, meaning the operational fire weather community has explicitly learned from the Marshall Fire and incorporated that learning into the warning system that is producing the corridor active right now. On February 26, 2024, the Smokehouse Creek Fire ignited in the Texas Panhandle. Within 12 hours, it had consumed approximately 500,000 acres. By the time it was contained, it had burned through approximately 1,074,000 acres, making it the second largest wildfire in US history. The Smokehouse Creek Fire killed 2 people directly and resulted in the loss of approximately 15,000 cattle. The conditions on the day of the ignition were extraordinary: sustained 60-mile-per-hour plus winds, single-digit relative humidity, and a fuel bed of cured grassland and rangeland that had been preconditioned by the Southern Plains drought of the prior season. The geography is, almost exactly, the geography that is currently under the most intense red flag warning in today's corridor. The Texas and Oklahoma Panhandle is the same county footprint where the Smokehouse Creek Fire propagated. The wind state, the humidity state, and the fuel state in that geography today either match or exceed the Smokehouse Creek conditions. The Carr Fire, which ignited on July 23, 2018, in Shasta County, California, near Redding, is the modern reference case for fire whirl behavior. The Carr Fire killed 8 people and destroyed approximately 1,500 structures. The most operationally significant feature of the fire was the development, on the afternoon of July 26th, of a fire whirl over the Whiskeytown area. The fire whirl, in post-event analysis, was rated at the equivalent of an EF3 tornado. It uprooted oak trees a meter in trunk diameter. It threw vehicles. It stripped asphalt off the road in patches. It killed Inspector Jeremy Stoke of the Redding Fire Department, who was sheltering in a fire engine that the whirl picked up and destroyed. The atmospheric column above the Carr Fire on the afternoon of July 26th was, in technical terms, Haynes Index 6. The Haynes Index is a fire weather metric that integrates lower atmospheric stability and moisture into a single number from 2 to 6. A Haynes Index of 6 indicates a dry, unstable atmospheric column capable of supporting plume-dominated fire growth, fire whirls, and pyrocumulus formation. The Carr Fire fire whirl is one of the clearest modern examples of what happens when an ignition occurs under Haynes 6 conditions. The Sacramento Valley today, with gusts to 50 miles per hour and humidity in the single digits, is forecast to operate under Haynes Index 5 to 6 conditions through Sunday night. The same atmospheric configuration that produced the Carr Fire fire whirl is, in structural terms, on the field today. The August Complex Fire, which began as a cluster of ignitions on August 16th and 17th, 2020, in Mendocino County, California, ultimately consumed approximately 1,032,000 acres, becoming the single largest fire in California history. The August Complex's most studied feature is its ignition cluster. Approximately 50% of the individual ignitions in the cluster were caused by a single dry lightning outbreak during the August 16th-17th window. The dry lightning outbreak placed thousands of cloud-to-ground strikes across the rugged terrain of the Mendocino National Forest and surrounding protected backcountry on dry fuel under wind. The ignitions cascaded. The fires merged. The merged fire complex became the August Complex. The reason this matters for today is that the Storm Prediction Center has, in this afternoon's Day 1 fire weather outlook, an isolated dry thunderstorm risk active over the red flag corridor. The same ignition mechanism that started the largest fire in California history is currently in the forecast for today. Whether or not today's dry thunderstorms produce the kind of cluster that the August 16th, 2020 event produced will be determined in the next 12 hours. When you put these case studies together, Campfire, Tubbs, Marshall, Smokehouse Creek, Carr, August Complex, you see a consistent operational signature. Wind in the moderate to high range, often with gusts in the 50s to over 100 miles per hour. Relative humidity in the single digits to low teens. A cured fuel matrix preconditioned by drought. a downslope or pressure gradient-driven wind regime, an atmospheric configuration that supports plume-dominated behavior, and in most cases an ignition source that was either electrical or natural lightning, on terrain where suppression resources could not arrive faster than the fire could propagate. That is the operational fingerprint. That fingerprint is, in every measurable dimension, on the field across 6 western states today. The honest scientific framing of what the historical reference class implies is this: the conditions corridor that opened on the morning of May 16th, 2026 is the same kind of corridor that has produced every major megafire of the past decade. The corridor extends through Monday night. The fuel underneath the corridor is at the 90th percentile of historical dryness for the date. The atmospheric column above the corridor is configured to support plume-dominated behavior across multiple sections, and the natural ignition source, dry lightning, is in the forecast. The conditions are not new. The corridor footprint is unusually wide for May. The drought baseline underneath is the deepest on the modern observational record, and the operational meteorological community is, in its public-facing language, saying, in the deliberately understated voice they always use, that this is the kind of regime that produces defining fire event. Whether or not that event occurs in any specific hour, on any specific ridge, in any specific drainage, is not predictable in advance. But whether or not the regime has the potential to produce that event is the question that the science answers in the data the National Weather Service is publishing this morning, and the answer is yes. The conditions are not the events. The conditions are the multiplier on whatever stochastic ignition source happens to find itself dropped on dry fuel under wind in the next 72 hours. The corridor is open. Somewhere in that corridor the ignition is going to happen. Part 5. Live Fuel. Moisture, Haynes Index and the ignition floor. If the previous part of this story has felt like it was building toward a single conclusion, it was, and the conclusion is the operational state of the fuel itself. Every fire weather analysis ultimately reduces to one question: how dry is the vegetation? Wind matters, humidity matters, atmospheric configuration matters. But the variable that fire behavior models put the most weight on, the variable that determines whether a given combination of wind and humidity will produce ignition and propagation, is fuel moisture. And the operational fuel moisture across the western United States right now is, in the technical language of the operational fire weather community, pre-staged for ignition. The operational metric for living vegetation is called live fuel moisture content, or LFMC. It is measured as the percentage of water in living plant material, expressed as a fraction of the plant's dry weight. So if you collect a sample of chaparral foliage, weigh it, dry it completely in a laboratory oven, weigh it again, and calculate the ratio, you get the live fuel moisture content. The number is interpretable on a standardized scale. A value above 100% indicates a seasonally healthy plant, carrying more water than dry mass, which is normal for chaparral in winter and early spring. A value between 80 and 100% indicates normal seasonal drying as the plant moves toward its summer baseline. A value between 60 and 80% indicates critical drying. The plant is shedding water faster than it is taking it up. The fuel is no longer biologically resistant to ignition, and a value below 60% indicates the ignition floor. Below 60%, the plant is operationally indistinguishable from dead fuel. Under any combination of wind, low humidity, and ignition source, the fuel will burn with explosive behavior. The California Department of Forestry and Fire Protection, known operationally as CAL FIRE, maintains a network of LFMC sampling sites across the state. Field crews physically collect samples on regular schedules and submit them for laboratory drying and analysis. The data is published, the values are interpretable, and the values being reported from chaparral ecosystems across Southern California by early May of 2026 are reportedly in the high 70s and low 80s% range. That value is normally not reached in Southern California chaparral until mid to late June. The fuel is curing approximately 6 weeks early. That 6-week early curing is the operational signature of the mega drought baseline plus the heat dome history of the past 2 months. The chaparral, the oak understory, the juniper pinyon woodland, all of these ecosystems are biologically tracking water availability through their root systems. When the soil column is empty, when the snowpack reservoir is exhausted, when the aquifer groundwater has been pulled down, the plants respond by shedding water from their leaves. The leaf water content drops. The live fuel moisture content drops. and the operational fire weather community begins to track the early curing signature as a leading indicator of fire potential. The early curing across the western United States this year is not subtle. It is large, it is documented, and it is on the input side of every fire behavior model that is being run for the operational forecasts you're reading this morning. The complementary metric is dead fuel moisture content, which tracks the water content of dead vegetation, fallen leaves, twigs, logs, grass cured by previous season dieback. Dead fuels are categorized by their time to equilibrium with ambient atmospheric humidity into 1-hour fuels, 10-hour fuels, 100-hour fuels, and 1,000-hour fuels. 1-hour fuels are the finest material, grass, small twigs, leaf litter, that respond to ambient humidity within an hour. 10-hour fuels are slightly larger material, like sticks up to about 1/4 inch in diameter. 100-hour fuels are intermediate, and 1,000-hour fuels are the heaviest material, logs and large branches that take days to equilibrate. Under today's regime, with relative humidity at 4% in the Texas Panhandle and 10 to 20% across most of the corridor, the 1-hour dead fuel moisture content has dropped below 2% across the warning footprint. 2%. That is, in practical terms, the operational floor for fine fuel moisture. Below 2%, the ignition probability from a single spark approaches 1. The 10-hour fuel moisture is in the 3 to 5% range. The 100-hour fuel moisture is in the 6 to 10% range. These are the values that the operational fire spread models input into their calculations, and the values across the corridor today produce model outputs of rapid spread rates, high flame lengths, and extreme rates of fire line intensity if ignition occurs. The energy release component, which is the metric that integrates fuel moisture across multiple size classes into a single number, expressing how much energy the fuel will release per unit area if ignited, is at the 90th percentile of the historical record for May 16th across the warning corridor. The 90th percentile means that, of all May 16ths in the modern record for this geography, only 10% had energy release component values as high as today's. So if you sampled the historical record, you would have to go back through approximately 10 Mays to find one with fuel as energetic as today's. The 90th percentile is, statistically, the operational threshold the National Interagency Fire Center uses to declare elevated fire potential. The 90th percentile is, on a fire weather day with single-digit humidity and gusts in the 50s to 70s, the kind of fuel state that produces the largest fires in the historical record. Today's fuel is at that percentile. The next layer above the fuel state is the atmospheric column itself. Fire behavior is not just determined by what is on the ground, it is also determined by what is above the ground. The atmospheric stability above a fire, meaning the temperature and humidity profile of the air column from the surface up to several kilometers, determines whether the fire's smoke and heat can rise efficiently into the upper atmosphere, or whether it stalls in a stable layer. A fire whose smoke column rises efficiently is plume-dominated. A plume-dominated fire generates its own atmospheric circulation, can sustain extreme rates of growth, can produce fire whirls, can spawn pyrocumulus clouds, and in extreme cases can spawn pyrocumulonimbus storms that generate their own dry lightning, which creates the feedback loop of a fire generating ignitions ahead of its own front. The metric that the operational fire weather community uses to predict atmospheric stability above a fire is the Haynes Index. The Haynes Index, named after the meteorologist who developed it in the late 1980s, integrates the stability of the lower atmosphere, typically the layer from the surface up to about 5 kilometers, with the moisture content of that layer into a single number ranging from 2 to 6. A value of 2 represents a moist, stable atmospheric column that would suppress fire growth and prevent significant smoke column development. A value of 6 represents a dry, unstable column that supports the most extreme plume-dominated behavior. The values from 3 to 5 are intermediate, representing the range that produces the bulk of modern wildfire activity. A Haynes Index of 6 is, in operational terms, the maximum risk classification. The Car Fire whirl on July 26, 2018, occurred under a Haynes Index 6. The campfire on November 8, 2018, ignited under Haynes 5 conditions and developed Haynes 6 conditions through the afternoon. The Tubbs fire on October 8, 2017, occurred under Haynes 6. The August complex fire spread phases through August and September of 2020 featured multiple days of Haines 6. The operational signature of a Haines 6 fire is plume-dominated. The fire generates its own circulation. The smoke column rises to 10 or 15 kilometers. The fire whirl risk is elevated. The pyrocumulus risk is elevated. The pyrocumulonimbus risk is elevated. The fire behaves not like a wildfire propagating through a fuel matrix, but like a thunderstorm propagating through a fuel matrix. The forecast atmospheric soundings for the Mojave Desert Slopes and the Sacramento Valley today are, under operational evaluation, Haines 5 to Haines 6. The trough plunging across the Intermountain West has produced a dry, unstable atmospheric column from the surface up through approximately 5 kilometers. The moisture content of the column is subtropical, meaning the air is unable to suppress fire column development through latent heat condensation. The temperature gradient is steep, meaning rising air parcels from a fire are unstable and continue rising. Under these conditions, the atmospheric column does not damp out a fire, it amplifies it. And if ignition occurs today on any of the fuel beds across the corridor, the atmospheric column is structured to support plume-dominated growth. The combination of single-digit humidity, gusts in the 50s to 70s, fuel moisture below the seasonal floor, dry lightning ignition risk, and Haines 5 to 6 atmospheric instability is the exact operational signature of every modern megafire. It is not one of the variables in the regime today, it is all of them, simultaneously, across 6 states. The atmospheric instability layer has a second consequence that is worth pausing on, because it connects to a research question that has been quietly accumulating in the climate attribution literature. When a large fire produces plume-dominated behavior, it injects substantial amounts of aerosol, smoke particles, soot, organic compounds, into the upper troposphere and lower stratosphere. Those aerosols have an effect on the local atmospheric circulation. They absorb solar radiation, they reduce surface heating in some configurations, they suppress boundary layer mixing. In some cases, they appear to extend the lifetime of the heat dome ridge that produced the conditions for the fire in the first place. This is a research question, not a settled conclusion. But the existing peer-reviewed literature includes papers that have documented, in regional case studies, the apparent extension of high-pressure ridge persistence following major smoke injection events. The mechanism is plausible: atmospheric absorption by aerosol, redistribution of solar heating, modification of the lapse rate above the smoke layer. The empirical record is mixed but not absent. The honest scientific position is that there is a plausible positive feedback mechanism by which a major wildfire under a heat dome ridge can incrementally prolong the heat dome ridge that produced it. This is the kind of feedback that the climate system scientific community calls a nonlinear amplifier. The system can locally entrench its own conditions through the consequences it generates. If a major fire ignites in the corridor today, the smoke production over the next 72 hours will be substantial. The combined fuel loading across the western United States, the favourable atmospheric column for plume-dominated injection, and the existing high-pressure configuration over the southwest all point in the direction of a smoke event that could reach the upper troposphere if the fire develops plume-dominated behaviour. Whether or not that smoke event then incrementally extends the high-pressure ridge over the corridor for additional days is a research question. But it is in the literature, it is a non-zero possibility, and it is one of the structural reasons that the operational fire weather community is watching today, not just for the immediate fire risk, but for the cascade of consequences that any major ignition would set into motion. The deepest scientific framing for what is happening today, then, is not a single variable. It is the layered convergence of multiple variables: drought baseline, snowpack collapse, fuel curing acceleration, atmospheric instability, dry lightning ignition risk, downslope wind physics, embercast potential, smoke feedback risk, into a single regime that is operationally indistinguishable from peak summer in mid-May. The corridor is open. The ignition floor is below the operational threshold. The atmospheric column is structured for plume-dominated behaviour. The natural ignition source is in the forecast. The historical reference class is unambiguous. The conditions corridor that is on the field today is the kind of corridor that produces the major fires of the era. Whether or not today is the day the corridor produces such a fire is not knowable in advance. The stochastic ignition source is, by its nature, not forecastable in detail. but the operational probability of a major ignition somewhere in the corridor over the next 72 hours is materially higher than the operational probability of any normal mid-May day. And the consequence layer, if ignition occurs, is structured by the case studies of the past decade. The fire that ignites under these conditions is not a small fire. The propagation through the embercast mechanism, the development under Haynes 5-6 instability, the spread through the cured fuel matrix under 30 to 70 mile/hour wind, all point in the direction of a major event. There is one more technical layer worth pausing on before we move to the human context part of the story, and it has to do with how fire spread rate scales non-linearly under the conditions we are looking at today. Fire behavior modeling typically uses a metric called rate of spread, expressed in chains per hour or meters per minute, which measures how fast the leading edge of the fire advances through the fuel. The rate of spread is not a linear function of wind. Under low wind conditions, the relationship is approximately linear, double the wind, double the spread rate. But under high wind conditions, the relationship becomes superlinear. Once wind speed exceeds approximately 40 miles per hour at the surface, the spread rate begins to accelerate faster than the wind itself, because the wind is doing additional aerodynamic work, preheating fuel ahead of the front, generating embercast that creates secondary ignitions ahead of the main fire, and producing the kind of firefront coherence that propagates as a wave rather than as a creeping line. Under the 70 mile/hour gust regime forecast for the Mojave slopes today, the rate of spread under the operational fuel moisture state would, in classical Rothermel equation-based modelling, exceed 5 miles per hour in cured grass and approach the upper end of the model's calibrated range. In chaparral, the spread rate would be slower, but the flame length would be substantially higher, with crown fire behavior triggered above approximately 8-foot flame lengths. Each of these operational thresholds, the rate of spread, the flame length, the crown fire trigger, produces different consequences for fire behavior management and for evacuation planning. Today's regime is, on the input side of the models, in territory that the model calibration data only thinly populates. The second technical layer is what fire behavior researchers call the probability of ignition, which is the probability that a given heat source applied to a given fuel bed, under given environmental conditions, will result in a self-sustaining ignition that propagates beyond the initial point. The probability of ignition is, in modern fire behavior science, a more useful operational metric than fuel moisture alone, because it integrates fuel moisture, ambient temperature, wind, and the energy characteristics of the heat source into a single probability value. Under typical mid-May conditions across the western United States, the probability of ignition from a single dropped match, calculated against grass fuels at the ambient moisture state, is in the range of 15 to 30%. Under today's conditions, with relative humidity at single digits, ambient temperature in the upper 80s to mid-90s, fuel moisture below 2% in the 1-hour class, and wind speed in the 20 to 30 range, the probability of ignition approaches 100%. Every match starts a fire today. Every spark from a piece of farm equipment starts a fire today. Every backfire from a poorly tuned engine starts a fire today. Every cigarette dropped from a vehicle window starts a fire today. The ignition floor has dropped to the lowest operational level the system measures. The third technical layer is what the National Fire Danger Rating System calls burning index, which integrates the energy release component, the spread component, and a fuel model coefficient into a single number that represents the difficulty of suppressing a fire if one ignites. Burning index values across the warning corridor today are in the high range of the system's scale. In practical terms, what this means is that the personnel and equipment requirements to contain a fire under today's conditions are substantially higher than the requirements under normal conditions. A fire that would, in normal conditions, be containable with a single engine company, and a hand crew might, under today's burning index, require multiple engine companies, multiple hand crews, aerial resources, and a unified command structure to bring to initial containment. The cascading resource demands of a single ignition under today's conditions can rapidly exceed the local response capability, which is part of why the federal fire management agencies have been pre-positioning resources for weeks. The fourth and final technical layer is the wind-driven fire spread phenomenon known as a fire run. A fire run is a phase of fire behavior during which the fire is propagating with sufficient organization and momentum that the rate of spread becomes essentially decoupled from the local terrain and fuel variability. Under sustained wind conditions, a fire entering a run can propagate for hours at rates exceeding the suppression community's ability to flank or pin the fire front. The Smokehouse Creek Fire's 500,000-acre advance in 12 hours, which we covered in the historical reference part of this video, was a single sustained fire run under 60-mile-per-hour wind. The Marshall Fire's progression through the Boulder County exurbs was a fire run under 100-mile-per-hour wind. The Camp Fire's destruction of Paradise was a fire run driven by embercast under 60-mile-per-hour wind. Under today's wind state across the corridor, any ignition that escapes initial attack is structurally pre-staged to enter a fire run within the first hour. The fire run mechanism is what converts an ignition into a megafire. So the question that lands, at the end of the technical layers, is the question we have been building toward through every part of this video. The science gave us the framework, the case studies gave us the reference class, the operational data gave us the today-specific snapshot, the conditions are loaded, the corridor is open, and somewhere in the next 72 hours the question of whether the corridor produces a defining event is going to be answered by some piece of stochastic ignition that no forecast can name in advance. Part 6. The Conspiracy Currents. What the science actually shows, and the one honest Steelman. Every time a major fire event hits the news cycle in the modern era, a particular set of alternative framing circulates in the corners of the internet that have decided the official explanation cannot be the whole story. Some of those framings are creative, some are paranoid, some are anchored in a real observation that has a mundane explanation, and one of them, the one we will get to at the end of this part, has a genuine peer-reviewed scientific substrate that almost nobody is talking about. Let's walk through the framings one at a time, deal with each honestly, and end where the science actually supports interesting follow-up questions. The first framing is the directed energy weapon theory. After the 2017 Tubbs fire, after the 2018 Camp Fire, after the 2023 Maui Lahaina fire, and after every major urban interface conflagration since, a recurring claim has emerged that the fires were not started by natural or accidental ignition sources, but by directed energy weapons deployed by some unspecified governmental or corporate actor. The framing typically cites three categories of photographic evidence. First, the apparent simultaneity of multiple ignitions within a small geographic area. Second, the observation that structures often burned while the vegetation immediately around them appeared intact. Third, the appearance of melted aluminum and other unusual metallurgical features in the post-fire wreckage. Let's deal with each of these honestly. The simultaneity of multiple ignitions is a real observation. In high wind, low humidity conditions, an ignition does not stay localized. The embercast mechanism, which we covered in the historical reference part of this video, distributes burning fragments across miles of wind-aligned terrain. A fire that started at a single point an hour earlier can be generating new ignitions miles ahead of the original front by the time anyone notices. To a person watching from the ground, or to a person reviewing aerial footage after the fact, the multiple ignitions look simultaneous. They are not. They are sequential, separated by the embercast travel time, which can be a matter of minutes for fragments travelling a few miles in 60-mile-per-hour wind. The simultaneity is illusory, an artifact of how fast the wind is carrying the fire. The observation that structures burn while nearby vegetation remains intact is also real, and it has a well-documented explanation. Modern residential construction uses materials, wood framing, asphalt shingles, vinyl siding, polyurethane foam insulation, that have very different ignition and combustion characteristics than living vegetation. Living ornamental vegetation, particularly irrigated landscaping, is typically carrying high moisture content, a structure that has been preheated by radiant flux from approaching flame, or that has been embered by burning fragments landing on its roof, can ignite and burn while the surrounding irrigated lawn and ornamental shrubs remain too moist to take ignition. This is not anomalous. It is the standard behaviour of urban interface fires. The Tubbs Fire's progression through the Coffee Park neighbourhood of Santa Rosa, the Camp Fire's progression through Paradise, the Lahaina Fire's progression through Front Street are all extensively documented examples of structure-to-structure propagation in the absence of significant vegetation burning between them. The mechanism is embercast plus radiant flux. It is not exotic. The melted aluminum observation is the most often cited piece of putative evidence. Aluminum, in standard industrial alloy form used in residential applications, window frames, vehicle bodies, light pole housings, has a melting point of approximately 660 degrees Celsius. Steel has a melting point of approximately 1500 degrees Celsius. Copper has a melting point of approximately 1080 degrees Celsius. A standard grass fire under flaming combustion of cured fine fuels regularly reaches flame temperatures of 800 to 1000 degrees Celsius at the flame front, with sustained temperatures in the post-flame combustion zone in the range of 600 to 800 degrees. A wildfire propagating through structures with the additional fuel load of structural lumber, polyurethane insulation, and synthetic furnishings can produce sustained temperatures well over 1000 degrees Celsius in localized hot zones. So aluminum melts, steel and copper do not. Glass deforms, concrete spalls. All of these features have been documented in post-fire forensic analysis going back many decades, and all of them are consistent with the temperature profile of standard wildfire combustion. The melted aluminum is the expected outcome of a wildfire reaching urban materials at standard flame temperatures. The directed energy weapon framing also has a basic operational problem. It requires the existence of weapon systems for which no credible operational evidence exists in any unclassified, declassified, or whistleblower record. It requires the existence of an actor with the motivation, the capability, and the operational opportunity to deploy such weapons at the scale required, repeatedly, across multiple geographies, over multiple years, without a single instance of the deployment being credibly documented, recorded, or whistleblown. And it requires that the consistent set of fire behavior features that the framing points to, features that are individually and collectively explained by standard wildfire physics, must be reinterpreted as evidence of an exotic mechanism when a more parsimonious explanation already covers them. The framing fails the standard parsimony test that scientific reasoning requires. It does not survive contact with the operational physics. The second framing is the smart city land grab theory. The claim is that major fires are deliberately allowed to destroy specific communities, Paradise, Lahaina, the wine country fire footprint, and others, to enable land transfer to corporate or governmental entities for high-density redevelopment, often framed as a smart city or 15-minute city agenda. The framing requires multiple coordinating actors across multiple events to operate without leak, across multiple jurisdictions, over years. The empirical record refutes the central premise on its face. Post-fire parcel tenure data show that the substantial majority of destroyed residential parcels in Paradise, in Lahaina, in Santa Rosa, and in the Marshall Fire footprint were either rebuilt by the original owners or remain in the original ownership pending insurance and reconstruction processes. The displacement of populations from these communities is real and tragic, but it traces to insurance market failures, to the financial inability of individuals to afford the cost of rebuilding under updated building codes, to housing market dynamics in surrounding communities, and to individual financial decisions about whether to remain. None of those trace to coordinated land transfer to specific identifiable entities. The framing also cannot account for why the largest fires of the past decade have predominantly burned across federal, state, and ranching land. Smokehouse Creek across Texas, Panhandle Ranchland, August Complex across Mendocino National Forest, and the surrounding protected backcountry, the Dixie Fire across the Lassen and Plumas National Forests. Terrain with no urban development pressure or smart city redevelopment potential. The third framing is the weather modification theory. The claim is that the upper-level trough driving today's wind regime is artificially induced, often citing HARP, geoengineering operations, or cloud seeding programs. The energy budget rebuttal to this framing is overwhelming. HARP is an ionospheric heating facility operating in the high-frequency radio band at frequencies between approximately 3 and 10 MHz. It is located in Gakona, Alaska. Its total power output, when fully operational, is approximately 3.6 megawatts. The facility's purpose is research into the ionosphere, the region of the atmosphere above approximately 70 kilometers in altitude, well above where weather occurs in the troposphere. The energy required to drive a continental-scale upper-level trough is on the order of 10 to the 25th joules, a quantity so far above HARP's 3.6 megawatt continuous output that the ratio is, in plain terms, approximately 10 to the 15th power. That is a factor of 1 quadrillion. There is no physical mechanism by which HARP can couple energy, into the tropospheric circulation at the scale required to produce the synoptic patterns the conspiracy framing attributes to it. A peer-reviewed analysis published in 2024 in the journal Communications, Earth and Environment by Yuan and collaborators directly addressed the HAARP and weather modification framings and demonstrated mathematically that no operational ionospheric heating technology can produce a measurable forcing on synoptic scale weather systems. The paper has been cited in this channel's coverage of related conspiracy framings repeatedly, and the conclusion is consistent across the climate science attribution literature. HAARP cannot do this. Cloud seeding programs, which are real and documented, operate by introducing condensation nuclei, silver iodide, potassium iodide, or salt particles, into existing clouds to encourage precipitation. They cannot create clouds where none exist. They cannot create the synoptic patterns that produce clouds. They cannot move the jet stream. The maximum precipitation enhancement that any peer-reviewed cloud seeding evaluation has demonstrated is in the range of 5 to 15% of the natural precipitation that would have otherwise fallen from the seeded cloud. That is not a continental scale weather modification capability. That is a marginal enhancement of pre-existing precipitation systems. The fourth framing is the solar-driven theory. The claim is that solar activity, coronal mass ejections, geomagnetic storms, high-speed solar wind streams, is driving terrestrial weather extremes, including today's wind regime. The current G2 geomagnetic storm from May 15th and 16th, the solar wind speed peaking at approximately 800 km per second, and the coronal hole high-speed stream affecting the magnetosphere are sometimes invoked as a partial driver of today's tropospheric weather. The scientific position on solar terrestrial coupling is well established. Solar activity does produce real effects on the upper atmosphere. Thermospheric expansion, ionospheric currents, induced ground currents in long power lines, satellite drag on low Earth orbit objects. But the energetic coupling to tropospheric weather circulation is at least 4 orders of magnitude below what would be required to drive a continental scale upper level trough. The trough you're seeing in the synoptic charts this morning is driven by Rossby wave dynamics in the mid-latitude jet stream, themselves driven by equator to pole temperature gradients, sea surface temperature anomalies, and the seasonal evolution of the polar vortex. All of these are tropospheric and oceanic processes. They are not solar processes. The G2 storm currently affecting the magnetosphere is interesting on its own terms. It produced aurora visibility in the northern tier of the United States. It created some satellite drag effects. It generated ground-induced currents that elevated the operational alert state for high-latitude power grids. But it is not driving the wind on the Mojave Desert Slopes today. The energetics do not work. Now, having walked through the 4 conspiracy framings and addressed each with the science that actually applies, let me end this part of the video where the conspiracy framings get unexpectedly interesting, at the one alternative framing that has a genuine peer-reviewed substrate. This is the honest Steelman, the claim that, in the colloquial conspiracy framing, sounds something like, the fires create the conditions that produce more fires. That framing, in its colloquial form, is overstated and not directly supported. But there is a real, peer-reviewed, actively published scientific hypothesis that is structurally similar and that the climate science community is taking seriously. The hypothesis is that the smoke aerosol produced by large wildfires under heat dome ridges can, in some configurations, locally suppress the boundary layer mixing process that normally limits ridge persistence, and thereby incrementally extend the lifetime of the high-pressure system that produced the fire-supportive conditions in the first place. The mechanism, in technical terms, works through the radiative properties of smoke aerosol. Smoke particles in the lower troposphere absorb incoming solar radiation. The absorption produces a temperature stratification. The smoke layer is heated, while the surface underneath is cooled relative to a smoke-free case. The stratification stabilizes the boundary layer. The stable boundary layer reduces vertical mixing. The reduced mixing reduces the rate at which the high-pressure ridge above is decompressed and dispersed. The ridge persists longer than it otherwise would. The conditions that produce the fire, heat, dryness, atmospheric subsidence, persist longer. The fire continues to produce smoke. The smoke continues to reinforce the ridge. This is not a confirmed mechanism in the sense that it has been demonstrated for any specific event with full causal attribution, but it is a research question framing that has appeared in multiple peer-reviewed publications over the past decade, and the mechanism is plausible based on the established atmospheric physics of aerosol radiation interaction. The research community calls this a nonlinear amplifier, a process by which the system can, under specific configurations, entrench its own conditions through the consequences it generates. If this framing turns out to be substantially correct, and the empirical record continues to accumulate, the implication for fire weather forecasting is significant. It means that a major fire event under a heat dome ridge is not just the consequence of the ridge. It is, in some sense, a contributor to the ridge. The ridge made the fire reinforces the ridge persists longer, the fire continues. The system enters a regime where the duration of the fire-supportive conditions is not just a function of upstream weather drivers, but is partially determined by the fire itself. This is the honest steelman. It is not a directed energy weapon. It is not a smart city land grab. It is not HARP. It is a non-linear amplification mechanism anchored in real atmospheric physics that the peer-reviewed literature is actively investigating. If a major fire ignites in today's corridor and produces a major smoke injection over the next 72 hours, the question of whether the ridge over the southwest is incrementally extended by that injection is one of the questions the climate science community will be asking in the post-event analysis. The answer is not known in advance. The mechanism is not fully characterized, but it is the version of fires intensify the conditions that produce fires that has actual scientific substrate, and it is worth taking seriously not as a conspiracy theory, but as an open research question. Now let's land where this all goes. The conditions are loaded, the corridor is open, the fuel is at the 90th percentile of dryness for May 16th. The atmospheric column is structured for plume-dominated behaviour. The natural ignition source is in the forecast. The historical reference class, Campfire, Tubbs, Marshall, Smokehouse Creek, Carr, August Complex, tells us what kind of consequence the regime is capable of producing if ignition occurs. The drought underneath extends through summer. The National Interagency Fire Center's Predictive Services Outlook projects above normal significant fire potential across most of the western United States for June, July and August. The fire season has not officially started. The fire season is not expected to be easier than today. The fire season is expected to be the multi-month version of today. What you are watching today is not a single event. It is the first delivery vehicle of a multi-month structural risk that the science has been telling us was coming for approximately a decade. Williams and Abatzoglu in 2019 on the vapor pressure deficit attribution. Abatzoglu and Williams in 2016 on the fuel aridity climate signal. Jolly in 2015 on the global fire weather season expansion. Williams, Cook and Smerdon in 2022 on the southwestern megadrought baseline. The papers were published. The papers were peer-reviewed. The conditions the papers predicted are on the field this morning across 6 states, with the ignition floor at 0 and the wind state at 70 miles per hour. The drought made the gun, the heat dome cured the fuel, the wind is here, the corridor is open, and the question we have to sit with, as a culture, as a country, as people watching this video from inside or outside the warning footprint, is the question that the science cannot answer in advance, but that the next 4 months are going to answer in detail. The conditions corridor that opened on May 16, 2026, is not going to close before the conditions corridor of June opens. The June corridor is not going to close before July's. The July corridor is the climatological peak, and the fuel underneath all of these corridors is already cured, already empty, already pre-staged in mid-May for what is supposed to be the worst part of August. Every megafire of the past decade ignited under conditions less severe than what is operationally active right now. The historical record does not give us any examples of a corridor of this footprint, this duration, this temporal anomaly, and this drought baseline that did not produce at least one defining event within the immediate window. The forecast extends through Monday. The summer extends through October. The conditions are not the events, but the conditions are the necessary precondition, and they are, by any operational measure, the most preloaded mid-May fire weather setup the modern observational record has on file. The 4-month structural risk that the science has been describing for a decade is, in concrete operational terms, what the next quarter of the calendar looks like for the western United States. June will deliver the climatological onset of the western fire weather season under fuel conditions that are already at peak summer levels, July will deliver the climatological peak of the western fire weather season under a mega-drought baseline that has not seen a meaningful precipitation event in months. August will deliver the second peak of the season, the August dry lightning window that the August complex fire of 2020 made famous, under fuel conditions that have, by that point, been operationally pre-staged for nearly 3 months. Each of those months has the structural capability to produce a defining fire event of the kind we covered in the historical reference part of this video. The cumulative probability of at least one such event occurring across the western United States between today and the end of August is, in any reasonable statistical framing, very high. This is the part that you have to sit with. Today is not the only day this is happening. Today is the beginning of a multi-month period during which days like today are going to be the operational baseline rather than the outlier. The June and July outlooks from the National Interagency Fire Center, published before today's corridor opened, projected exactly this. The outlook from the Predictive Services Group at NIFC's National Multi-Agency Coordination Center for Geographic Area Coordination Centers across the western United States projected above normal significant fire potential across most of the West for June, July and August. The outlook is not new, the outlook has been published since early spring. The May 16th corridor is the first major operational verification of the outlook, but the outlook does not stop in May, it continues through August. The conditions corridor that opened this morning is the leading edge of a multi-month structural risk that the science has been describing since at least the Williams and Cook and Smerdon 2022 megadrought paper. There is a deeper philosophical question embedded in all of this, and it is worth naming, because the channel that is producing this video has spent a substantial amount of its catalogue working through it. The question is what it means to be the inhabitants of a planet whose climate system is undergoing measurable, attributable, peer-reviewed structural change, while the public discourse about what that change actually is and what it operationally implies has not caught up. The vapor pressure deficit increase across the western United States is documented. The expansion of the fire weather window is documented. The southwestern megadrought is documented. The early season fire weather corridor is documented in real time on the National Weather Service maps that you can pull up right now on your phone. None of this is hypothetical. None of this is forecast. None of this is being predicted by climate models that someone might quibble with. The data is the data. The operational meteorological community is publishing its discussions in plain language. The science behind those discussions has been published in major journals for a decade. And yet, the cultural and political response to the conditions on the field this afternoon is, in most quarters, unchanged from what it would have been on a normal May. The news cycle is going to cover other stories. The weather coverage that does mention the fire weather corridor will likely lead with the wind, will note the warnings, and will move on. The structural significance of the regime, the fact that fire weather conditions are now operationally a 6 weeks early phenomenon, the fact that the corridor footprint is continental in scale, the fact that the underlying megadrought baseline has shifted the system into a configuration that the historical record does not give us reference points for, will not be the lead in most coverage. The audience watching this video is one of the few audiences that has been receiving the structural framing in real time, and that is, in the deepest sense, the reason this channel exists. There is one final thing worth saying as we close. The operational fire weather community, the climate attribution research community, the National Interagency Fire Center, the National Weather Service offices that issued the warnings active right now, none of these are alarmist organizations. They are conservative, evidence-based, institutionally cautious, operational and scientific groups whose primary discipline is the careful documentation of empirical reality. When the consensus of that community is that today is the leading edge of a multi-month structural risk, and that the underlying climate signal is real and attributable and ongoing, that consensus is not a prediction. That consensus is a description of the operational state of the system as those groups measure it, in real time this morning. The conditions are what they are. The corridor is open, and the fire season, by every operational measure we have, has already started, whether or not the calendar is willing to admit it. So if the conditions are this loaded in May, and the drought is going to last through August, and the fire season hasn't started yet, what does the rest of this year actually look like? And at what point do we stop calling it a season at all?